Hi. In the previous lecture, we have learned the key idea of mutation testing. We can use mutants to assess the quality of our test code. For quality, we mean the fault detection capability of the test suite. Mutants are artificial defects or changes applied to the production code. Then, the test suite is executed against those changes to assess whether the test results change as well. One big question left open regards the size of the mutants. How significant should the changes be? Should we change one single line? Should we alter multiple lines? Furthermore, what type of changes should we apply? Mutation testing is based on two hypotheses. The first is the competent programmer hypothesis, which states that, given a specification, a competent developer develops a program that is either correct or different from the correct program by a combination of simple errors. The second hypothesis is the coupling effect. It states that the test cases that detect simple type of faults can also discover more complex formal faults. In other words, simple faults are coupled to other more complex faults. Based on these two hypotheses, we can conclude that our mutations to the production code should be small. This is because small faults are more realistic based on the competent programmer hypothesis. And second, if our test suite can detect small faults or mutants, then it can also identify more complex mutants that are actually coupled to the simple ones. Therefore, a mutant is typically defined as follows. Given a program P, a mutant P' is obtained by introducing a simple syntactic change to the program. Here, a syntactic change is a small change to the production code that makes the mutated code still valid. In other words, the code should be compilable. How do we define a change? We should not opt for any change. Instead, we should consider only alteration to the production code that mimic typical human mistakes or glitches. To better explain this concept, let us consider this small class in Java. We are interested in the method invert, which returns a fraction where the numerator and the denominator are swapped. Besides, there are three conditions to check some corner case, like for example when the numerator is 0. In that case, the fraction cannot be inverted. Now, let us consider a coverage-adequate test suite. This suite reaches 100% of branch and statement coverage, and all test cases have assertions and don't fail. Notice that the fourth test case asserts whether the expected exception is actually thrown using JUnit 5. One possible mistake a competent developer could make is to forget the sign minus when inverting the fraction and changing the sign of both the numerator and the denominator. This small nuisance is highlighted in red color in the slides. And this is a very tiny syntactic change to the original code. Thus, our test suite detects this change. If we run our tests, we discover that the second test case fails. Therefore, we would say that the mutant is killed. Another possible mistake in the production code regards the constant in the first if condition. For example, we may use the wrong constant, 1 instead of 0, as highlighted in red color. Does our test suite detect the mutants? Well, let's rerun our test suite. As you can notice, the first test case failed when executed against the mutant while it passed when executed against the original program. Once again, our test suite seems to be adequate. Up to now, we have seen how to create mutants by manually mutating the production code. Clearly, this methodology is not practical nor efficient. For this reason, it is a common practice to rely on tools that generate mutants automatically. The mutants are created using the so-called mutation operators. Mutation operators are grammatical rules that apply syntactic changes to the production code. We can distinguish two categories of operators. The first category is represented by operators that mimics the effects seen in the past for the same program. The mutants seen in the previous example can be indeed generated using this type of operators. The second type of operators is language-specific, like, for example, operators that alter the inheritance in Java or operators that change pointers of operation in C code. Nowadays, most of existing mutation tools provide basic mutation operators that alter parts of the code that are common among most of programming languages, such as arithmetic or relational statement in the code. The most classic mutation operator is the arithmetic operator replacement, which replaces arithmetic operation such as the addition or the division in alternative operators. For example, in this Java method, we have two arithmetic operations, the division and the module. Each of these two operations can be replaced with any other arithmetic operation. For example, the division can be replaced with 4 alternative arithmetic operations as well as the module. The arithmetic operator replacement also includes the case where the operation is completely dropped and replaced with one of the two operands. In our example, we can replace the division between E and B with either A or B. Another traditional mutation operator is the relational operator replacement, which replaces a relational operator in the code with an alternative one. In our example, we have only one relational operator, equal, and it can be replaced with 5 different operations. Therefore, this mutation operator would produce 5 mutants for this small method. The conditional operator replacement mutates the condition operators in the code, like, for example, the logic AND and the logic OR, the short circuits in Java, as well as unary relational operators. All programming languages have assignment operators. That's why one of the most common mutation operators is the assignment operator replacement. Such an operator generates mutants by replacing an assignment operator with an alternative one. In our example, we have only 2 assignments. Each one can be replaced by many alternative operators in Java, and that's why in this case we show only a few alternatives. The last basic mutation operator is the scalar value variable replacement. With this operator, each variable reference is replaced with another variable reference of the same type. To make the code meaningful, the new variable reference must be declared before the location where the mutation is inserted. In our example, we have 8 locations that can be mutated. In the if condition, we can replace the variable b with the variable a, which is the only one defined at that point in the code. In the last line, the variable quotient can be replaced by all variables already defined in the code, like a, b, and remainder. In Java, there are many other language-specific operators. For example, in Java, mutants can be obtained by changing the access modifiers to methods and attributes, by removing method overriding, or changing the declaration type of the variables. We are not going into the detail of all mutation operators for Java. However, at this stage, you should have a clear idea about how mutation operator works and why.